So thank you all for coming this evening. It's great to see everyone. I'm Associate Professor Edward Obbard. I'm the Director of the UNSW Nuclear Innovation Centre, and I'm an academic in the School of Mechanical and Manufacturing Engineering at UNSW Sydney. So I'm going to start by acknowledging the traditional custodians of the land where we meet today, who are the Gadigal people. I'd like to pay my respects to their elders, both past and present, and extend that respect to any other Aboriginal or Torres Strait Islander people who may be here this evening. I've got a fair bit to say this evening, but first of all I'm going to hand over to our Dean of Engineering, Professor Julian Epps, to introduce this evening.
Thank you very much for the kind introduction, Ed. It's my great pleasure to say just a few words before this exciting discussion gets underway. Some of you may know, in fact, that UNSW's first Vice-Chancellor was a nuclear physicist, and also that UNSW was home to a nuclear engineering program until about the 1980s. So although UNSW's current Master of Engineering Science in Nuclear Engineering and its associated research program are only about 9 years old, they build on a strong history in this area. And it's no surprise that UNSW aims to be a driving force for nuclear engineering education and research. In November 2023, we established the Nuclear Innovation Centre, a cross-disciplinary, cross-institutional hub for advancing Australia's nuclear engineering and science education and its research capability as well. The centre brings UNSW's scale to nuclear through the Faculty of Engineering, which is the largest and highest ranked of its kind in Australia, through the combined efforts of all of UNSW's faculties, which are also very large, and through UNSW's industry and research collaborators. We have many of these. So as well as scale, nuclear innovation and nuclear safety in particular demands excellence. And again, I think UNSW brings a proud history of excellence. World-changing technologies like silicon photovoltaics for clean energy, polymer membranes for clean water, quantum computing, and much more. Building on this scale and excellence, the Nuclear Innovation Centre aims to ensure the development and the growth of a skilled workforce, including future leaders in nuclear science and engineering. I think discussions like the one that we're about to hear with distinguished Professor Jacopo Buongiorno help to provide international context and great technical depth to inform and I think encourage us to pursue these aims and also to forge new collaborations. With that, I'll pass back to Ed. Thank you.
So this evening we've got this special guest from the United States, Professor Jacopo Buongiorno. So Jacopo is the Tepco Professor of Nuclear Science and Engineering at the Massachusetts Institute of Technology, which we all know as MIT. And he's also the Director for the Centre of Advanced Nuclear Energy Systems. So I'm particularly interested in that role, seeing as I've just taken on something similar at UNSW. And also the Director of Science and Technology of the MIT Nuclear Research Reactor, which is really exciting. MIT has a reactor right in the middle of campus. He has published over 100 journal articles in the area of reactor safety and design, two-phase flow and heat transfer, and nanofluid technology. For his research work and teaching, he has won several awards, among which recently the 2022 ANS Presidential Citation. ANS is the American Nuclear Society. Professor Buongiorno is a consultant for the nuclear industry in the area of reactor thermal hydraulics and a member of the accrediting board of the National Academy of Nuclear Training. He is also a fellow of the American Nuclear Society, a fellow of the Nuclear Reactor Thermal Hydraulics Conference, a member of the Australian Society of Mechanical Engineers, and a past member of the Naval Studies Board and a participant in the Defence Science Study Group. So you can see he is completely esteemed across actually very many areas of nuclear engineering in the United States. So in Australia, it's been a bit of a roller coaster over the last couple of years, hasn't it? In September 2021, we announced the AUKUS partnership, well, the government announced the AUKUS partnership with the United States and the UK. We are planning to own, operate, maintain and regulate nuclear submarines by the early 2030s. Fortunately, we have an ongoing history of research reactor operation in Australia, with the Opal reactor continuously producing nuclear medicine and offering nuclear research capabilities. And there's great bipartisan support politically for our submarine program. However, support for nuclear energy is rather divided amongst the two main political parties. So that is the kind of context in which we meet this evening. So about this event, it's an in-conversation event. So I will be simply asking some questions and chatting with Jacopo about his discipline and about nuclear science and technology in America and potentially in Australia. So, and you'll be able to submit questions to Slido. Is that clear to everybody? And I will try to weave them into our discussion. So for now, I'm just going to welcome Professor Buongiorno.
And thanks for the introduction. You said that I'm a member of the Australian Society of Mechanical Engineers.
Oh, did I?
It's the
I'm
American
sorry.
Society of Mechanical Engineers. But
That
now
was a
that you've
mistake.
mentioned it, I should consider it. That will give me an additional excuse to come here and visit. So,
Okay, slip up. Thank you.
oh, now it should be on. I shouldn't repeat the joke, though. That's fine.
So, Jacopo, I mean, to begin with, I'd really like just to hear about your research.
Yeah, so I'm truly a nuclear nerd. I've been in this discipline, this very exciting discipline, for close to 30 years. When I came close to the end of high school and it was time to choose what would I do in college, I was torn literally between classical literature and engineering. And with a little bit of a gentle push from my parents, I suppose in the right direction, I chose rather wisely engineering. But then the process was not over because I had to choose what flavor of engineering to get into. And so you guys obviously know mechanical, chemical, materials, nuclear and all of that. And I gravitated towards nuclear for two reasons that are going to sound fairly superficial, but remember I was 18. First, it sounded by far the coolest of all the different flavors. And number two, it had quite clearly a rigor and a challenge in the curriculum that really appealed to me. And I, here I am 30 years later, and I teach classes in nuclear engineering. I've done a ton of research, and I'm getting to the answer to your question in a second. And I still think it's the coolest flavor of engineering, so no regrets there. So now, what kind of research do I do? Well, for the greatest part of my career, I've been having a lot of fun in designing nuclear reactors that have certain attractive features. Some might operate at a high temperature to get a higher efficiency of conversion of heat to electricity. Others might do something interesting with the fuel cycle. There are some designs that help you to, for example, reduce the level of waste because they burn waste as part of their normal process, and so on. And then roughly 10 years ago, I had the privilege of running a study on the future of nuclear energy in a carbon-constrained world. So this was a broad look at the prospects of nuclear in this new world where we all want to decarbonize our energy system and also have energy security and all of that. And it was a little bit of an epiphany because when you look at why nuclear hasn't grown globally as much as it could, and I would argue should, given its many merits, it has very little to do with the design of the reactors, all the nitty-gritty things. And it has everything to do with things like project management or economics or business models or applications, et cetera, et cetera. And so as of 10 years ago, my research has gone from something very, very technical that is related really to the design of the reactors, to the systems, to a broader attention to how do we change the development and delivery and business models of nuclear to make it successful in the marketplace. And that has led me to applications of nuclear energy which are beyond the traditional domain, which would be the power grid, the electric grid, and towards things like industrial processes or desalination or propulsion. You mentioned AUKUS in your introduction. Of course, that's a major application of nuclear and so on. So with my students, we look at a lot of these, let's call them softer aspects, but in fact, they're very, very important. I would say essential to the success of nuclear going forward.
Yeah, really interesting. I mean, one of your innovations, which I followed some years ago, and I was really impressed by, actually before I knew you, was the floating nuclear reactor. Like these big, like floating oil platforms, right, which would have a really large scale, like gigawatt scale reactor inside this sort of floating oil platform. Tell us about that.
Yeah, that was one of the most fun projects actually I work on, because I had to learn a lot about naval engineering or marine engineering as well as nuclear. So if you look at the recent history of a new nuclear construction in places like the US and Western Europe, you'll see that projects that were started, say, 10, 15 years ago have been plagued with cost overruns and schedule delays. And you start wondering why. What does it have to do? Does it have to do with the fact that the technologies are new? Is there some kind of innovation that has gotten in the way? And the answer is absolutely no. It has everything to do with the fact that, at least in countries like the US and Western Europe, large construction sites, which is the traditional way in which nuclear power plants are built, are very inefficient, very low productivity environments. And this is, by the way, true for all sorts of large infrastructure projects, or people call them mega projects, whether it's bridges or transmission lines, etc. Everything that exceeds a certain size in terms of cost and complexity tend to be affected by cost overruns and schedule delays. And so the idea of this floating nuclear plant is to shift the construction of a plant, of a nuclear reactor and its surrounding structures, from a construction site, a land-based construction sites, to a shipyard. And shipyard, unlike construction sites, are high productivity, very efficient environments. The same as factories. Think about the shipyard as the marine equivalent of factories. And so the central idea of this concept of the floating reactor is, can I integrate a nuclear reactor into a floating platform or a barge and build the whole thing in a shipyard? And that's expected to reduce cost. And on top of that, it makes the whole delivery of the system to a site much more efficient, because you can literally then float it to the coastal point, to the coast, to the location where it's going to be used. And this might sound far-fetched, might sound sort of a little futuristic, but I ask you to consider two things. First, for the past 60 years, we've been operating nuclear power plants at sea. We call them submarines and aircraft carriers. They have a fantastic record of performance and safety. And number two, in the civilian domain, there is currently at least one example of a floating nuclear power plant. It's the Akademik Lomonosov. It's a Russian design that was commissioned in the St. Petersburg shipyard back in 2019, and has been operating quite successful at a town called Pevek, which is a community on the northern slope of Siberia. And so they literally floated in the power plant. It's now docked at at that site and provides heat and electricity to that small town, which is a mining site up there. So I think that model, all our opinions on Russia aside, I would say, is quite attractive. It could reduce cost. It could make nuclear more versatile. A challenge that we have, I think, going forward is to make nuclear look more like a service and a product, and less like a mega project. And I think this approach can help.
Yeah. So are SMRs partly solving that problem?
Well, SMRs go in the right direction. Now, we need to understand it's not going to be a silver bullet and solve all the challenges, both perceived and real, that nuclear is known for. If you look at projects in Asia, South Korea, China, I'm talking about new construction projects of nuclear plants in places like China, South Korea, even Japan before they had the accident, India and Russia itself. They are able to deliver these large, traditional, gigawatt scale, very large plants on time and on budget. So to them, the idea to go to smaller reactors at the moment doesn't seem particularly attractive. But if you look at, as I said earlier, the recent history of construction in the West, Western Europe and the United States, you've had these large construction sites, these big projects that have gone, twice as long as they were supposed to and cost 3 times as much. So I would say the main value proposition of these smaller machines smaller physically, less complex, and therefore in absolute terms less costly, is to reduce the financial risk and the project risk. Now, the jury is still very much out on whether the cost of energy generated by this small reactor is going to be higher or lower than large plants. There is a reason why historically the industry has gone towards larger and larger reactors, because they are more efficient. Okay, so now we're doing something a little bit different, but it's to reduce the project cost, the project risk, and the investment risk, really.
What I worry about...
but just let me add more. So that is, in my opinion, the main value proposition of these smaller systems, but it's not the whole picture. You also have certain applications where you don't need a gigawatt. You don't need 1,000 megawatt. A couple of hundred megawatts, in some cases even 10 megawatt or even less, is the right fit. So just like in the US, I understand that here there is a lot of interest in replacing coal-fired plants that are going out of business because of or being decommissioned for environmental reasons or other reasons, because they reach the end of their lifetime, with nuclear power plants. Now, coal-fired plants, the individual units, are not typically 1,000 megawatt or 1,600 megawatts. They tend to be 200, 300, 400 megawatts. So if you want to slot in a reactor and use some of the existing infrastructure at those sites, you can reuse transmission lines, you can reuse cooling infrastructure, you can use access roads, administrative buildings, you can re-employ the workforce, maintain that economic activity at those sites, then the smaller reactors might be a better fit. So there is also a benefit in that sense.
What I sometimes worry about with SMRs is they may just be a point on the journey towards a fully deployable reactor. Because if a reactor could ever be fully deployable, then maybe you wouldn't need the workforce where you deployed it as well. And that could be even cheaper. So do you think SMRs, given that they haven't really been adopted yet, they may in fact be kind of a work in progress rather than a completely finished solution?
Yeah, for sure. And also you can do modular, you can shift scope of project from the evil construction side to the beneficial factories and shipyards, even with larger reactors. And so the whole idea of modular construction is to shift from an approach where you bring in raw materials and individual components to a site and then you start assembling the plant at the site, to one in which you pre-assemble large modules, again in a high productivity environment, whether factories or shipyards, and then ship off to the site large modules and then connect them. And this approach actually is not new to nuclear, because if you look at the ABWR, Advanced Boiling Water Reactor series in Japan between the early 2000s and the 2010-12, they actually used modularity and modular construction. They were successful in bringing down cost and schedule by roughly 20%. And those reactors were not small. They were actually 1,300 megawatts, 1.3 gigawatts. So I think, indeed, SMRs have a lot of benefits, as I said earlier. The interest now is to sort of reduce the scope of the project so that you don't bet the company when you start the project. It's not a $10 billion thing. It's maybe a couple of $1 billion. But whether SMR is the optimum going forward remains to be seen.
Yeah, so, talking of betting the company, what happened to NuScale at Idaho Falls project, which was cancelled just November last year? Do you have a bit of insight about, the kind of process and what happened and what potentially went wrong?
Yeah. So I think the nature of the customer, so first of all, for those of you who are not following sort of the daily news on nuclear, right? So NuScale is a some people call it a startup. It's not really a startup because they've been around for close to 20 years, I think at least 15 years when it was incorporated. And they've been developing one of these small modular reactors. And they had seemingly secured a project in Idaho that would deploy, I think, 6 modules, so 6 small reactors at a single site. And the customer was going to be a consortium of municipal electric utilities in Idaho and Utah. And I forgot the number, but it was several dozens of micro utilities, all of which had to sort of sign up for this project. So they had to be approved by a lot of different stakeholders, and that was the first flaw, that it was not sort of a consolidated effort, one. And number two, this is a consortium of utilities that had zero previous experience with nuclear. Okay, so in the US we have 100 reactors, we have less than 20 utilities that have been owning and operating those reactors for 30, 40, 50 years. Those utilities in many ways know what they're getting into because they're experienced with nuclear. This particular customer did not. And so what they were doing, they were basically buying a product. They were buying a plant without being properly engaged and understanding cost, risk, and eventually, the burden of having to operate a large nuclear power plant. So I think that what really happened was, the customer wasn't ready. Certainly was not the ideal customer for this project. And then, if I may say, maybe a little bit more on the technical side, NuScale has done a very good job. This is the name of the company once again, at modularizing and miniaturizing the reactor itself. If you're even vaguely familiar with what a nuclear power plant looks like, you got the reactor proper. That's where the fission reaction takes place. That's where the energy is generated. But then you have all sorts of other systems that are required to turn that heat, that energy that comes out of a reactor, into electricity. And then, of course, you got safety systems, and then you have structures, et cetera, et cetera. And so NuScale has done a good job at miniaturizing and modularizing the reactor itself, but they would put these modules into a gigantic reinforced concrete structure. Some people call it the big swimming pool, that if built would be the largest reinforced concrete structure in the world, actually, man-made, right? And so, and we find, and we found when we analyzed, and I'm sure NuScale are acutely aware of this, that most of the cost of the final plant would not be in the reactors themselves, but in the building, in that reinforced concrete building itself. So what happened in the past couple of years, you guys know, the cost of commodities, steel and concrete, has gone through the roof. And so when that happened, all sorts of technologies are going to be affected. But one that is so reliant on concrete, steel, et cetera, like NuScale, was particularly affected. And so the cost estimates went through the roof. And at that point, that customer, which in my opinion wasn't ready to begin with, said, I'm out. So I think that's...
My goodness, it comes back to
what
concrete,
happened.
doesn't it? It's
crazy, isn't it? Yeah.
Wasn't that what went wrong at Olkiluoto in Finland as well?
It was one of the many things.
They
that
had
went
problem
wrong,
making the concrete flat, didn't they, in Finland, and they had to go back and dig it all out.
Right. So this goes back to what I said at the beginning. It's so frustrating as a nuclear engineer. I wish the real problems were neutronics, fuels, materials, sensors, the high-tech stuff.
Yeah.
The real problem with nuclear is how do you build the damn thing, right? So concrete, foundations, pipe fitting, welding. I mean, it's the mundane stuff that you got to get right. And again, that's why there is so much value in trying to come up with designs or approaches that really take that risk, that construction risk out.
Wow, yeah. Did we have any questions about that before I move on? Or not yet? I'm
answering too quickly here.
No, it's okay. No, we're doing well. We got time actually. It's nice.
Cool.
Yeah. So look, we're talking about the United States and technology. So I did also want to ask you about just technological development in nuclear engineering in the United States, because another really exciting project, which is hitting the ground, is TerraPower.
Yeah.
Isn't it? And that, again, going back to your research about the sort of wider implications, the business model, the staffing, the grid connection, the concrete, maybe, is a new take on that, isn't it? So could you tell us a bit about that TerraPower project and really the kind of concept and what they're trying to do there?
Yeah. So first I would say, for the first time in many years, we have several projects that are effectively launched in the US and Canada. I should put Canada in the mix, in North America. And they're all based on these new technologies. There are many different flavors, and so I'm going to sort of try to unpack it. Before I get to TerraPower, the one that I want to mention is taking place at the Darlington site in Ontario, OPG, Ontario Power Generation. That's actually a small modular reactor, 300 megawatts, which is based on well-known technologies, a boiling water reactor, which we've been using for 60 years, but is being repackaged and shrunk down to a physical size and to a power output, which enable this sort of more nimble construction approach. And so that's ongoing. OPG, the utility itself, is a very experienced nuclear operator. They are a very serious partner for the vendor, which is General Electric Hitachi. So I have high hopes that project is going to look a lot healthier than the NuScale project that we just discussed a second ago. Then now to TerraPower. TerraPower is of course, the company created by Bill Gates, so everybody knows this. And their reactor is actually not that innovative. It's a sodium-cooled reactor, which may sound exotic, but in fact, if you look at the history of nuclear technology, you go back to the 1950s, one of the first reactor designs that were demonstrated in the US and in Russia at that time was the sodium-cooled fast breeder reactor, which is, at that time, was exotic, I suppose. You could do something funny with the fuel cycle. But not much has changed in terms of the design, and TerraPower has adopted that. The innovation of TerraPower is as follows. What they do, nuclear reactors are expensive machines that burn cheap fuel. It takes a lot of money to build the plant. Once the plant is built, to run it is relatively cheap. So you want to run a nuclear reactor always at 100% power. It's, from an economic point of view, is rather attractive, okay? But on the other end, what do we know about the grid these days? It used to be that they want base load, always 100% power. But now you got, wind, solar, demand goes up and down. So you can't, by necessity in certain markets, you are not almost like allowed to just give 100% power all the time. You got to go up and down and so on. So one trick to sort of keep together these two requirements, you want to run your reactor always at maximum power, but you want to give power up, but you want to give electricity output to go up and down, is to actually store on site the heat. Because a nuclear reactor is a heat source. So you run it 100% power, you take the heat and you put it in two tanks of liquid salt. One is cold, one is hot. It's a little bit like what is done in concentrated solar power plants. And so when the grid does not demand a lot of electricity, you're not producing a lot of electricity, you're accumulating energy in one of those, in the hot salt tank. And then when the grid demands more electricity, you start extracting more heat from that salt, and you convert that heat to electricity and you sell it to the grid. Okay, so now that all sounds good. In practice, how does it work? They've gone to a site in southwest Wyoming that is called Kemmerer. It's the site of an existing coal-fired plant which is going out of business because of environmental reasons. And they're going to slot in this TerraPower reactor, which is sized to have more or less the same power output of the coal. And the reason why they're doing it at that site is because it's on a big transmission line that connects Wyoming to California. What do we know about California? They have a lot of sun, a lot of solar, which is great when the sun shines, but it's not that great when it doesn't. And so the prices of electricity in California go up and down wildly during the day. So the plan for this nuclear power plant in Wyoming is to basically sell more electricity to California when the prices are up and sell less when the prices are low. And they can do this with this little trick of the heat storage. So by their calculation, I'm told, they're confident that single-handedly doubles the revenue of that nuclear power plant. Everything else been the same, right? So the cost of the plant is what it is, but they plan to get twice as much money because of this, sell high and keep the electricity when the prices are low.
Yeah, is it being built now?
Yeah, so that is it's under construction in terms of site preparation. They have started to engage with the NRC, the Nuclear Regulatory Commission, so the licensing process is coming along. It's a private-public partnership in a sense that the Department of Energy is paying for half of the project. The other half is private money from Bill Gates and friends. For those of you who know the financial markets, Warren Buffett, another big name, of course, is a co-investor of Bill Gates. So yes, that's ongoing. The third project that I want to mention that I'm excited about is called X-Energy, and it's yet another reactor type. And without getting into too many details, suffices to say that this reactor can operate at very high temperature. So it generates heat at 750, 800 degrees C. By comparison, traditional reactors generate heat at around 300 degrees C. So what's the value proposition? What's beneficial about generating heat at higher temperature? Well, you got two benefits. The first is because of the laws of thermodynamics, the conversion of heat to electricity is more efficient if the heat input is at a high temperature. So you get a more efficient process. But perhaps more importantly, this plant is going to be co-located with the Dow Chemical plant that requires a lot of heat and electricity to make chemicals. And so it's the first example, at least in the United States, but I think worldwide, that is going to demonstrate the use of nuclear reactors to decarbonize a chemical plant. And it's going to be co-located, right? You can transmit electricity over long distances, but you cannot do the same thing with heat. So your nuclear plant, which produces heat, has to be very close to the chemical plant. And this is taking place at a place called Seadrift, which is on the Gulf Coast in Texas. So those are the three that are ongoing now.
Great. Yeah, I mean, we were talking earlier about the TerraPower one. It seems that they've been lucky enough to land on the main distribution line of power from their state down to California. Right?
Yeah,
so
but
that's part of the business, right?
It's part of the business model, right? Yeah, but there is more to the story for TerraPower, which I think is also interesting information for this audience, and that is the way they chose that particular site is that yes, it was on that transmission line. They had identified 4 coal-fired plants in Wyoming that are going out of business, and then instead of saying I want to be here or here or here, they actually opened it up and said which towns, which site wants it, and so there was. This might be counterintuitive because we're used to think that people are opposed to nuclear. They're not as opposed as we think. And in fact, there was a surge of interest and say, I want it, and then they eventually picked that one because of this business of being on the transmission line. But there was a little bit of a sort of a competition to actually host the nuclear power plant, and primarily I think it's because of the positive economic impact that a nuclear power plant can have on the local communities.
Well, we've got a question here. I'll ask a couple of questions coming in. So this is a financial one. Is the biggest gap towards nuclear deployment the lack of experienced project finance professionals and sophisticated investors linking with the nuclear industry?
I think that's part of the problem. It's not. There is also a very real issue associated with maturity of the supply chain, and once again, I keep sort of hitting you on the head with this, and also the ability of the industry to manage large projects. So there is the financing piece, but there is also the execution, and there is supply chain. And then in the United States, there is also the relative inefficiency of the regulator. But I don't want to overplay that, because you find people in my community that will say it's all the NRC fault. If they only could get on board with the plan and license these nuclear plants fast, all problems would go away. No, a lot of the issues related to cost overruns and schedule delays are self-inflicted wounds by the industry.
Yeah, on SMRs as well. We had a question submitted before the event, about safety, about SMR safety. I mean, I guess I'll kind of build on it a little bit and ask, we all talk about SMRs being, being completely accident resistant. It's impossible to have an accident in an SMR. Is that true, or is it more my view? I think is maybe that you can have an accident, but the accident is tolerable.
It's definitely the latter.
What's your view on that? Do you want to expand on that?
Emphatically, any system or machine that is designed by human beings can fail in some way. So there is no such thing as an accident-free reactor or an accident-free engineer system. They can all fail. The question is exactly as you pose it: is what are the consequences of failure? Okay, and so through the use of intrinsic safety features, through the use of what we call passive safety systems, which means systems that don't rely on external energy sources like pumps or diesel generators, etc., you can increase the reliability of the system to the point where, one, the likelihood of an accident, of course, is decreased. Again, you can't make it zero, but you can decrease it substantially. And number two, the consequences of that accident are much milder. And that's exactly where we are. And the exciting thing is that of course, the exact design matters, but we're seeing vendors and technology and reactor technology developers coming up with all sorts of different designs that take this approach, whether it's a light water reactor or a sodium reactor or a molten salt reactors. They all seem to share at this point that philosophy that drives down the likelihood of abnormal events or accidents, and importantly, they minimize the consequences of it in terms of radiological release, public health impact, and all of that. And the practical implication of this is that, for example, for these new reactors that are going to be deployed in the U.S., the 3 projects that I just mentioned, U.S. and Canada, what we call emergency planning zone which for traditional reactors, it's a 10-mile radius area, pretty large. This is not an exclusion zone. People live there. You have towns, you have businesses, etc. But if you live within that emergency planning zone, then you need to be periodically trained in order to know what to do in case of, to respond to an emergency or things like that. So obviously that creates stress and cost. Now, for all these new technologies, the Nuclear Regulatory Commission, the regulator, has approved a methodology that allows the emergency planning zone to be shrunk down to site boundary. So if you decide your site boundary is 100 meters around the reactor, then that's it. That's your emergency planning zone. So if you have a town that is half a kilometer away from the plant, even under the worst case scenario, they don't have to evacuate. They don't have to take iodine pills or the horror show that we're used to for traditional plants. So I think that's real progress in terms of social acceptability of the technology.
Yeah, I mean, in terms of progress, so nuclear technology is making progress. Somebody called Steve has a question that says, energy technologies are moving at such a pace not previously seen, but how can nuclear compete with other technologies like solar and wind in terms of this progress, this velocity of change?
Yeah. So again, I think the race towards smaller machines could also accelerate the pace of innovation for nuclear. There is a product innovation cycle which has a real cost and a real schedule associated with it. If the complexity of your machine or of your system is smaller, you can go through innovation cycles quicker. Is it ever going to be as quick as an iPhone every 2 years or a year and a half or so we get a new model? Probably not. But I think we shouldn't think in terms of multi-decadal innovations, but more like 5 or 6 years for nuclear reactors. Having said that, now the bigger question is competition between nuclear and renewables. I really dislike the narrative of pitting them against each other. They are actually work together rather well. It's not either nuclear or renewables, but all the studies that we've done and many others have done show that the generation mix that gives you the decarbonization targets that we're interested in, so deep decarbonization, for example, the power grid or other sectors of the economy, rely on a balanced mix of nuclear and renewables, and also, frankly, a little bit of storage, because you still need to accommodate that almost like instantaneous intermittency and variability, which is introduced by the renewables. So it's really a combination of both. I would urge people to think in terms of a balanced portfolio of energy resources. Even if I had it my way, I wouldn't recommend 100% nuclear.
Yeah, and that's actually your research, isn't it? I mean, you've produced research outcomes that relate to those kind of balanced mixes.
Yeah, correct. And we've looked at many different regions, including South Australia, because I was asked by a colleague to do South Australia. And so we've applied the same model that we apply for regions of the US, China, and Europe to South Australia. And sure enough, even for this neck of the woods here, you find that if you want to deeply decarbonize the electric grid in that area, a mix of nuclear, wind, and solar is actually the best option.
Yeah. So we've got quite a few questions coming through, and I'm interested too, actually, in Australia. So because we've got a great foreign person here, we can have hypothetical discussions about, let's imagine, right, that we were going to deploy some nuclear energy in Australia. With all, that experience and lessons and, knowledge about economic models and technology that you've been experimenting with in the United States and through MIT, what would you do? What technology would you pick?
Okay.
How would you do it? What about the question of the mix of renewable and storage and nuclear? I know it's a difficult question, but surely we can talk about it.
Yeah, right? We can certainly talk about it. And I'm not going to pick technologies because I don't think it would be fair. But so I understand. First of all, there are some legal impediments that have to be removed. Or prohibitions, bans, etc. I would say that's the first of several steps. In other words, another one is to take advantage of what's happening elsewhere in the world. Like we talk about North America, there's quite a bit going on in Europe as well. And so projects are underway. And I think a very cost-effective a way for Australia to develop capabilities to sort of embed people in those projects. It's not a big investment. You're talking about prospective regulators, Australian regulators, spending a number of years in US, Canada, or France, or wherever it is that the projects are underway, and really learn deeply the technology, so that if at one point Australia decides to pull the trigger on a nuclear program, you don't start from scratch. So there is a lot that can be absorbed there. And I'm, given the historical ties between Australia and Europe, and Australia and North America, I know for a fact that, for example, the reactor vendors would love to have a prospective customer and stakeholders in Australia be part of the project. Now, as far as technologies are concerned, instead of picking individual reactor designs, or let me just sort of think in terms of broad classes, right? So for the grid, because of the desire to minimize financial risk, and also because of the desire to replace coal with nuclear, I think the SMRs, broadly speaking, do make sense. As I said at the beginning, it's unclear if the levelized cost of electricity of an SMR is going to be higher or lower than a gigawatt reactor. But in terms of what I just said, it makes sense for the grid. But then there are all sorts of other applications, even in Australia, that will not require an SMR, that they might need something else. And so you may have factories that require heat and electricity, and they may need at the level of, 10, 15, maybe up to 100 megawatts. So that gets us into a different class of reactors, which people call microreactors. So tiny little machines that generate maybe 5, 10 megawatts. And those are pretty exciting systems, because they can be entirely built in factories and then transported in one piece or a couple of modules to the site, and then they're sort of plug and play, and they give you heat and electricity. So it's a very nimble process. And an additional feature of these microreactors that I like is that these customers, think about, you have a factory where you need heat for some process. You're making steel or concrete or glass or whatever it is, or aluminum. And you want the energy, and you want it to be carbon-free, and you want it to be reliable and hopefully affordable. But the last thing on your mind is to turn your company into a nuclear operator and your site into a nuclear site. And so here, the business model probably ought to be power purchase agreement with a company that manages a fleet of these microreactors and sells electricity and heat as a service to paying customers. And because these systems, these microreactors, are transportable, you can envision that when it's time to refuel them, as high energy density as nuclear is, at one point you got to take the spent fuel out and put in fresh fuel. You don't do it at the site, so there is no handling and no storing spent fuel, which people call waste, at the site. But you do it at a centralized facility, because you can literally send back your microreactor to a central facility where it's open up, defueled, refueled, and then sent back to you, or sent back to another customer. So sort of a highly standardized fleet type approach. So that may make sense also for
the deployable reactor.
Yeah, in that case, literally is deployable reactor. Yeah,
okay.
And it obviates the need for transmission, for a lot of energy transfer infrastructure, because you don't need pipelines, you don't need transmission really, because it's all co-located, right? Energy source and energy user are at the same site.
Yeah, so this will. Obviously nuclear energy particularly is a very kind of hotly contested subject. Somebody in the audience is asking, what's the perceived risk with nuclear power? Why do you think some people perceive a great risk with it?
Well, I suppose my opinion is as good as anybody else's here. It's not a technical question, right? So if you look at the history of nuclear, I think the original scene, so to speak, is the conflation of nuclear energy with nuclear weapons. I think that's probably where the fear originated, and so that didn't help. If you look historically, now obviously the two industries are well separated, and then of course there have been a few high-profile accidents which have gotten a lot of negative coverage in the media. One thing I will say about, I'm obviously referring to 3 Mile Island, Chernobyl, Fukushima, and all of that. One thing I will say about accidents is as painful as they have been and as badly as they have affected, for example, the attractiveness of nuclear and set back the industry and cost a lot of money, et cetera, there have also been great learning experiences. And so just like all other industries, when there is a major event, a major adverse event, there are lessons learned that are then integrated into future practices or current practices. And all the nuclear plants, for example, are retrofitted and upgraded all the time as a result of the lessons learned from these accidents. So
Yeah.
it's true for all technologies, right? If you think
Each
about
accident does-
cars or airplanes, it's becoming safer and safer as a result of failures, and the same is true for nuclear.
It really happens, doesn't it? We know each accident is tumultuous and terrible, but it does transform the industry each time.
Yeah.
It really has, doesn't it? So I also wanted to ask you, Jacopo, we're talking about, I guess, sort of social impact and public policy and so on. But because you've done so much work in this area, I wanted to ask you for, an example or a case study or something where you've been personally involved, where you've been able to make a really positive change to this relationship between, say, policymakers and public and technologists and engineers, where you've really been able to, make that conversation happen.
Yeah, that's a great question. My favorite example that I've lived through personally is the Diablo Canyon nuclear power plant in California. So California at the moment has one big nuclear power plant, is 2 reactors, 2,200 megawatts. It's a large nuclear plant, and provides, I think, 7 or 8% of California's electricity and roughly 15% of its carbon-free electricity. So it's a big, it's actually the single largest generator in California. And it has a history of opposition from locals and state level stakeholders that goes back to the day when it was built in the late 70s and then became operational in the mid 80s. And in 2019, a coalition of so-called environmentalists, along with the state of California, decided that at the expiration of the current license for Diablo Canyon, the plant would be permanently shut down. And 2024 now, and next year was going to be the expiration date. And so 4 years ago, I decided, along with colleagues at Stanford, and you appreciate the combination of MIT and Stanford, at least reputationally, is pretty good. And we decided to run a study that would look at the economic and environmental value of this plant for California if its license was extended by an additional 20 years, which is, by the way, the standard extension that the NRC, the Nuclear Regulatory Commission, grants, following, of course, a very thorough review of safety and all of that. And what we found out is that whether the plant is simply kept online as a power generator for the grid, or its power output is used partially for desalinating water, and you appreciate California as a water scarcity issue, big time, lots of droughts, or whether part of the power output of that plant is used for hydrogen generation to be used in the transportation sector, the value is enormous. And we quantified that value literally in terms of billions of dollars, the economic value, and the environmental value in terms of millions of tons of CO2 avoided if that plant were to be extended. And so we published that report in November of 2021. And then I hired a PR firm in Sacramento, very knowledgeable, very well plugged into the whole political system in California. And they line up for us a series of briefings, starting with the governor's office, all the way down to the worker unions, the tribal leaders, business associations, media, et cetera, et cetera. And at the end of this process, we managed to restart the conversation about Diablo Canyon. At that point, we created enough momentum that a lot of other stakeholders came in, and then that's where I stopped taking credit. But to make a long story short, less than a year later, the California legislature voted overwhelmingly, it was something like 57-3, to allow the owner and operator of Diablo Canyon to apply for the extension of the license. And they said at least 5 years, but I think everybody assumes that eventually they're going to go to 20 years. So that's one of the things that I'm most proud of, frankly, in my career. It wasn't, from a technical point of view, we weren't solving differential equations. It wasn't a very nerdy, typical engineering project. We were quantifying the value of this plant. But the fact that at the end of that process, I can see that a nuclear power plant, which was to be shut down, is now going to be extended, has all this value, environmentally, economically, that's very gratifying. So I think that's probably the best example I can think of.
Yeah, thanks. I love that example that, we talk about cost of electricity, but isn't the cost of an currently operating nuclear plant, the cost of that electricity is about the cheapest electricity you can find anywhere?
Yeah, it pretty much is. So I already used the phrase, nuclear reactors are expensive machines burning cheap fuel.
Yeah.
It is true, right? So it costs a lot of money to build the plant. Once you build the plant and you paid it back, right, which from an economic, financial point of view, it may take 15, 20 years, whatever it is, the deal you have with your investors. Then the operating cost, the generation cost drops quite dramatically, and then nuclear is extremely competitive. And if you think about nuclear power plants being now licensed for 60 years to begin with, and most likely being able to go from 60 to 80 years, we have a few plants that have been already extended from 60 to 80 years, then you see the long-term value of these assets is enormous. And it is firm, as they say, a controllable, dispatchable electricity, and it's carbon-free 24/7. So it's pretty neat.
Yeah. So in that case study, as a successful, wow, what a story of social impact. We talk about social impact in our university. That's enormous social impact. But what made it work as that engagement between government, academia, public stakeholders? Because I'm sure it happens a lot, but doesn't work, right? So what was it about your study that made it so particularly influential and that made the outcome so clear?
Well, a couple of things. I like to think the quality of the study was very high. We were solid. Yeah. The numbers were solid, well justified, and all of that. I already mentioned the PR firm. The PR firm was absolutely key. I mean, the ability to have the right connections within the California stakeholder community and identifying influential people that, if persuaded that it's a good idea, will take action. That was absolutely key. But last but not least, the willingness of the governor, the legislature, and all these stakeholders to listen and reopen the conversation was key. And I don't think they did it just because they liked us. Yeah. They did it because from the time the decision to shut down Diablo Canyon was made to the time our report came up, a lot of things that happened had changed in California. First of all, they had blackouts. They were going down breakneck speed down the path of 100% renewables, shutting down plants left and right, and they had a lot of reliability issues on the grid. Number two, big droughts, which require water. Number three, very aggressive decarbonization targets for both the grid, the transportation sector, and all of a sudden realizing, okay, we got all these lofty goals on the table, but we have no clue how to meet them, right? Yeah. So I think we came in at the right time and tell them, look, the first step towards these goals is not to take a huge step backward and shut down your largest clean electricity generator. I think that resonated quite a bit. But then, each stakeholder, of course, has its own reasons for liking the New Deal, so to speak. The unions, for example, love the fact that, hey, here is 1,000+ workers. These are very well-paid jobs. And, well, they were going to end in 2024, 2025. Now they can go on another 20 years. So they like it for that reason, for example. So
so timing, stakeholders, high-quality research, and urgency to solve a problem, right? I guess are the main things, sounds like. Thank you. Well, in Australia again, we've got this enormous challenge to train something like 20,000 people for a submarine workforce. And we're working on it at UNSW. We're training nuclear engineers and we're doing nuclear research, and we're trying to scale up, right? We're trying to kind of do what you do at MIT. I don't know, what's most important? How do we grow the scale of our programs and attract more students and, become, well, certainly the national leading nuclear engineering university, but maybe somewhere in the world too?
Yeah. Well, first I would say, we compare notes at lunchtime, so I know our program is a bit bigger than yours. Yeah. But as big, so to speak, as our program is, it's a drop in the ocean of what is needed here. 20,000 people is a lot of people. Yeah. Now the good news is that 20,000 people doesn't mean 20,000 nuclear engineers. Certainly not 20,000 masters or PhDs, right? So the AUKUS program is going to need a lot of people with trades and crafts and engineer degrees, not necessarily graduate degrees. And so these are welders, electricians, pipe fitters, instrumentation and control, electrical engineers, et cetera, et cetera. So you should, you and ASA, the Australian Submarine Agency, and everybody involved should think about these holistically. It's not just the nuclear engineers, et cetera. But I think, you know the system here much better than me, so I'm not going to give you any suggestions. But the stars are aligned, right? So the AUKUS is going to happen. The ASA has been established. I understand they have a budget. They have a serious budget for the human resources development. They've already started to allocate some of that money to universities, and so it's now up to you to create a program that attracts people. I would imagine that of all states, New South Wales has probably the largest basis in terms of potential students coming in for nuclear and these other disciplines that are required. So
we have a lot of students, but not yet in nuclear engineering. Thanks. So look, we're nearly at the end. It won't hurt if we finish a couple of minutes early. But we do have a few minutes left. I thought I'd like to give you the last word, Jacopo. I mean, you've been in Australia for a while. We've had a discussion. Do you want to say something sort of meaningful to finish up for us?
No pressure. It has to be brilliant. It has to be meaningful. Well, at a minimum, I hope the conversation continues, so I will have an excuse to come back.
Excellent.
On a regular basis. I really love Australia. I was telling you, this is the fourth time I come. Usually there is a substantial vacation piece to it, and this time was no exception. And then there is a work piece, which is what we're doing now. But my personal view aside, I think if you look at the potential benefits that this technology can have for Australia, and direct benefits in terms of becoming part of the energy infrastructure, but also indirect benefits in terms of business opportunities. Australia already produces and exports quite a bit of uranium, for example. That could become bigger, but there could be other parts of the nuclear enterprise that could flourish in Australia. At a minimum, you owe it to yourself to leave the door open to this conversation. And so this business of bans and prohibitions, they have their history, and I don't know it. But it seems to me absurd that you would tie your hands and prevent yourself from even having that conversation and exploring that option. Then at one point you need to make a decision. If it makes sense, you go for it. If you don't, you don't. But I think now it's the time to get ready for the moment when you'll have to make a decision, yes or no. But you can't procrastinate. If you wait another 10 years to even do these early steps, then you miss the boat. Then this technology option will no longer be as compelling as it is between now and the next 10 years. So.
Yeah, interesting. Thank you. So thanks for this evening.
My pleasure. Thank you for having me.
Thank you.